Large samples, you calculate z-scores because large samples, it's easier to calculate with the standard bell curve normal distribution. It's kind of the bottom line. All right, so that aside, the calculation is on the bottom of page 297, and boy, it's a nasty one. Now, z-star, I like to call it the calculated z-score, z-star, is the difference in the populations, P1 minus P2, divided by the square root of P1 parentheses 100 minus P1 divided by N1 plus P2 parentheses 100 minus P2 divided by N2. Well, I altered the book formula in a couple of ways, and I want to explain what I did. You know, the book formula, of course, is correct, but so is mine. In the book formula, they have minus parentheses pi 1 minus pi 2. Well, in the null hypothesis, these would be equal. And so if you subtract them, you'll get 0, won't you? So if you're testing whether there's a difference or not, then you're testing versus a no difference and some kind of statistical, at least significant difference. So in almost all cases, when you're doing this kind of comparison, you would put a 0 here because these would be equal. So it could get complicated if you say, well, I want to test to see if there's a 10% difference between these two. Okay, if there's a 10% difference, then you would have these subtracted equals a 10%, and you would have 10% right there. So anyway, I don't mean to confuse the issue, but I'd say for our purposes, you can ignore the pi 1 minus pi 2 over there. Now, the more important difference is I use 100. And so the book formula will work if you're in decimals instead of percentages. So if you're in decimals, then 100% is the same as 1. If you're using percentages, better make sure those are hundreds. Got that? Okay. So I'm going to do some erasing so I can plug the numbers in. I wrote out the formula for z star with the numbers plugged in. So it would be the difference in these two percentages, 57.6 minus 46.0. 57.6, and then 100 minus this number is 42.4. And then the sample size was 2332. Now I didn't write down that the sample size for the men was 2,332, but that's what it is. That's how many men were there. So that number goes there. Similarly over here we have the women's number 46.0, its complement 54.0, and their sample size 959. So there's the calculation, and now it's time to warm up those calculators and work it out. So I'm going to, personally I'm going to calculate the denominator without the square root first. I'm going to enter it exactly as I see it. So here are my steps. 57.6 times 42.4 divided by 2,332 plus 46 times 54 divided by 959, and then I hit equal. So if you enter it in this order, your scientific calculator will do the correct calculation. I got 3.664, we'll round up to. Now I'm going to take the square root, and by the way, I do the square root on my calculator. I use the power key raised to the 0.5. So a 0.5 exponent would be square root. Hit equal. My denominator is around 1.91. Now, you know, I'm keeping all the decimals on my calculator. That keeps the final answer more accurate. I'm not going to round anything off till I get to the end. So I'm using all of my decimals. Now on top, I'm going to enter left parentheses 57.6 minus 46.0, right parentheses, and divide by the answer I got previously, so I use the answer button, hit equal, and I get 6.08. So the most accurate calculation you can do on this z-score is 6.08. So what do you make about what do you make of that number 6.08 for a z-score? You know, that's the number of standard deviations associated with this difference. And 6 standard deviations, you should recall, is humongous. It's extremely large. Too large for your textbook. So I don't have to look at the textbook, but if you look on page 649, it only goes up to a z-score, I think 3.89. And then above that, the p-value would be less than 0.0001. So from that chart, this is off the chart, the p-value would be less than 0.0001, less than 1 out of 10,000. Well, incidentally, just a curiosity, many calculators wouldn't even be able to calculate the p-value from such a high z-score. Because you need hundreds of places in order to calculate that using calculus. Well, you don't need to know that, fortunately. You can just look it up in the chart. Well, what's our conclusion? You see, the odds, or the chance that we would take samples this large and find this great a difference, when in fact in the population there is no difference between men and women, the odds of that happening are actually considerably less than 1 out of 10,000. So what do? We reject the null hypothesis. So, right at our conclusion, we reject null hypothesis with a p-value less than 0.0001. We are at least, or more than, at least 99.99% confident. How's that for confidence? Confident. And I get that number from subtracting from 1. 1 minus this number is 0.9999, 4 nines, 99.99%. We are at least 99.99% confident that the non-graduation rate for male athletes, and I'll reread this because it's getting a little sloppy here, is greater than the females. Alright, I'm going to reread that. It's a little bit sloppy and I don't feel like rewriting it. We reject null hypothesis with a p-value less than 0.001. We are at least 99.99% confident that the non-graduation rate for male athletes is greater than the females. Put a little apostrophe there. Alright, so this sample is very decisive. And it's showing that there's a difference between the two percentages because of the very low p-value or very high z-score. Okay, so that concludes all the worked out examples I have for you in this chapter. I have some more video looking at some journal articles, and I'll go over that next.